Welcome back to Release Radar. I'm Chris Biscardi, and today we're looking at the alpha release of Lucy Lang. Lucy is a new DSL or domain-specific language for describing finite state machines and state charts. It compiles to JavaScript using xstate. There are two big pieces of this explanation to understand: what a DSL is and what finite state machines are. A DSL is a domain-specific language. This is in contrast to general-purpose languages like Rust, JavaScript, and Python. While you can pretty much do anything in a general-purpose language, actually doing that thing may feel unergonomic or be prone to errors. A domain-specific language is able to use stricter compilers and custom syntax because it applies to specific use cases. Other examples of DSLs are protocol buffers and SQL. In this case, the DSL Lucy provides is defining finite state machines in a way that it can compile to JavaScript code that is compatible with the xstate JavaScript library. Which leads us to what are finite state machines. When developing an application, it's common to have different pieces be in different states at different times. This is the reality of developing an application. Sometimes we cobble together these states without defining them well, and end up with objects that can hold data from other states, older states, or transition into new states that we shouldn't be able to get into from the current state that we're in. Finite state machines are a way of defining what states there are and which ones we can go to next. In this visual example, we're showing the states and transitions for an API request. The boxes represent states the request can be in, and the arrows represent which actions can send us to which specific next states. We start out in this idle state. When we initiate the fetch to the API, we go into the loading state, which invokes the HTTP request while we wait. When it returns, it will either fire the done or error actions, sending us to either the resolved or rejected states. Xstate is a library for defining these state machines in JavaScript, whereas in comparison, Lucy is a custom DSL for defining them that compiles to the xstate representation that we would have written manually. There are a couple of ways to install Lucy. We're going to get started with the binary. When installing, it's important to note that Lucy has chosen LC as the name for its binary, and that a binary named LC already exists on Macs and Linux computers, which is the mono-license compiler. Due to this, I'll be aliasing the binary to Lucy. There are other integrations such as rollup and Veep, but we'll be keeping ourselves to the binary today to focus on Lucy and not integration. Speaking of the binary, it turns out the entire project is written in C and compiled to WASM. This is a really interesting architectural choice and reflects the general move in JavaScript tooling from JavaScript implementations to compiled languages like Rust and Golang, or in this case, C. If we run Lucy help or LC help, we can see that we've successfully installed this binary. There are a number of options, including operating on an entire directory or specifying remote import URLs. In this video, we're using version 0.1.4, which is an alpha release. I only have a couple of Lucy files in this directory, but as you can see, running the binary on the entire directory executes extremely quickly, faster than even you'd expect the startup for a JavaScript script. This is how we've compiled the Lucy DSL to JavaScript files we can use in our project. In my opinion, the DSL itself is pretty readable. We get keywords to create machines, as well as other keywords to declare states, and additional syntax for different things. In this case, we've got a machine named toggle machine with two states. These states are named on and off, just like you'd expect a toggle button to be, like a light switch or a toggle switch that you might see on an iOS device. We can receive a toggle event and transition to another state using this fat arrow syntax. In this case, if we're in the on state and we receive a toggle event, we're going to transition to the off state. And in the off state, the opposite will happen, and we'll transition to the on state. When we check out the compiled JavaScript file, we can see that create machine was imported from xstate and used to create our toggle machine export. The contents of the machine are a little bit more confusing to read, but only because we've used on as the name of one of our states, and on is also used to define what should happen in the case of certain events. Overall, I'm pretty happy with the DSL to JavaScript conversion. I find both pretty readable, but the DSL definitely wins when it comes to removing this extra object boilerplate. You may be wondering, as I did, how this works when integrated with existing JavaScript code. I'm used to writing my xstate machines by hand, which is pretty verbose as we just saw, but I also get access to all of JavaScript to do it, and xstate has a fairly expansive API service. One major design decision here is that basically all of that logic that I would normally write in just JavaScript now needs to be used as an import in the machines. I'm not terribly upset at this decision because I think it could lead to more understandable state machine files, and I find that stacking different states together in JavaScript objects makes them pretty hard to read. If we look at the imports, we can see that there's a custom import style used. which is fine, but I do wonder if there are going to be either more targets or compatibility with libraries other than XState to justify the difference between this and the ES module's import syntax. If we move on to the machines, we can see that we can define as many machines in a single file as we want to. So we have two machines here. One is a to-do item and one is our app. The to-do item machine has 3 states, including some new syntax for a final state. There's the idle state, the deleting state, and the final state deleted. Also notice the call to invoke, which means that when we enter the delete state, we'll run delete to do, and when it's done, transition to the deleted state. The app machine is where we get to see a little bit more of the fancier usage and calls to XState APIs you might be familiar with if you've worked with it before. Our app only has one state, the idle state. When a new to-do event comes in, we assign the context.todo value to a spawned to-do item machine. Learning the ins and outs of these specific syntaxes is going to be the major goal for deep Lucy usage, as far as I can tell. For example, we can only call spawn within assign. When a delete event comes in, we send a delete event to the to-do machine that we stored on context. That event will transition the to-do item machine into a deleting state, as seen in the idle state of the to-do item. The code this compiles to is quite a bit larger than we saw before. We can see that spawn, send, and assign, the new XState APIs that we took advantage of in the use API example, are now imported from XState. Also notice that we've compiled use API delete to do to import delete to do from API. As we might expect, we've got our 3 states, idle, deleting, and deleted, and we can see a one-to-one correspondence between invoke in our JavaScript file and invoke in the Lucy file. There's a couple of small differences. We don't have source, and we're using onDone in the JavaScript file, whereas in the Lucy file we're using done, but it's a fairly straightforward translation. In the app machine, we see our idle state and the 2 events that we need to respond to, new and delete. You can see that the logic is very similar, and we use the assign as well as the spawn calls in basically the same way that we did in the Lucy file, except that we're passing in an object here now. So it's a little bit more clear that we're defining a to-do main inside of this object, which is stored in the XState context for the machine. This makes it a little bit more obvious about how we're actually getting this delete to send to the to-do machine, because we now see that we've stored it in the context as to-do. So when we get the delete event, we can access it off to-do as well. I'm not going to talk about everything here, especially since Lucy is still in an alpha state, and different facets could still change before stable release. For example, there's syntax for an implicit machine file that I couldn't actually get to compile via the binary that you can see here on the page. A single file could theoretically have a state without having a machine defined, and the compiled JavaScript would create that machine and export it as the default export. There are a few worthy notes here though, in that delay is built in to Lucy, as well as the fact that there's a VS Code extension. You may have noticed when I was showing Lucy files earlier that they were all syntax highlighted. If you open a Lucy file in your VS Code, it will ask you to install the Lucy extension, and I think that this makes the alpha feel really polished. Overall, I think Lucy is a great project to pay attention to as it develops, but it's not a project that you might want to introduce into your production environments today.